There are some equations in this talk, but they're not very complicated, I promise you, so hopefully the blood rush to the stomach doesn't put you right to sleep. We'll try and walk through them. But first I wanted to introduce my lab. I do not have pictures yet of my new students, but they're both here, Christina front and center and Alec in the back, so say hi to them. Also in my lab, Tracy Shaw, who most of you probably know by now, a research associate and keeps the lab humming. She's submitted 4 papers to a special issue on euphausids recently, so she's been very busy. Also new to the lab is Andreas Fahlman. He's a courtesy research faculty here, just starting, and he's a marine mammal, well, marine vertebrate physiologist, so he uses tags, and let me get back to him in just a minute. Alyssa Andres is hiding from the hurricane up in Connecticut, I think, so she is not here, but she's a shark enthusiast. And Alexander Burns is here as well, right here. And she is studying some of the things I'll talk about today in shrimps, local Gulf of Mexico shrimps. So Andreas uses a combination of physiology and whole animal metrics as well as modeling to look at diving behavior in vertebrates. And yesterday, or Wednesday I guess it was, I had the opportunity to go to SeaWorld in Orlando where he was measuring heart rates in pilot whales. So that's pilot whale there with suction cups with electrodes stuck to them to measure like an EKG of the heart, and he's found that with every breath their heart rate speeds up and then slows down over time, which is, people have always interpreted a diving reflex in mammals, and he's showing that it's not specific to diving. They do it with every breath, and he thinks that they actually have active control over their heart like we have active control over our breathing. So interesting stuff coming out there. So he'll be around. We also talked about testing some of the ideas that I'll talk about in dolphins. So we're going to hopefully go to Hawaii, where he's got trainers that can make dolphins swim to their maximum ability, and you put a little device over the blowhole and measure the oxygen that they're consuming as they're swimming actively. So that sounds like fun. So the idea of critical oxygen is, it's an issue of a gradient from the environment so through the gills, the blood, into the cells, and then eventually to the mitochondria, where oxygen is used to produce ATP, which fuels all of our various activities. If you're at sea level, you've got air-saturated water, or in this case, atmospheric partial pressure of oxygen in air, and you have a large gradient from the environment down to the cells. If you're at high altitude, that gradient is reduced, or if you're deep in the ocean where oxygen is lower, that gradient is reduced. And so it becomes trickier to get the oxygen to the mitochondria where it's required. So one index of hypoxia tolerance has always been the critical oxygen partial pressure, and I've been measuring this since graduate school. Basically, you put an animal in a chamber and allow it to consume the oxygen gradually over time, and they maintain, it's usually measured in a resting or basal state, so they maintain a constant rate of oxygen consumption down to some critical low level, and then they can no longer maintain that rate. So the oxygen consumption rate falls off at that point. And over this regulation point, the heart rate is increasing, ventilation is increasing, there are adjustments in the acid-base physiology of the blood and adjustments to the mitochondria to better enable oxygen to be utilized. So if you increase the temperature or swim faster, your metabolic rate goes up and that critical oxygen level will be higher. Ocean deoxygenation, which is another climate-related problem, reduces the environmental oxygen and so forces animals below their resting critical oxygen level potentially. So these ideas have been around for a very long time, and they've been largely unchanged for over a century. So Hill and colleagues first measured maximum metabolic rate in humans. This is before they'd even invented stationary bicycles and treadmills, I guess. So They have bags of air that they're breathing from and into different bags of air, and then they go back to the lab and measure the oxygen content in those bags. Fred Fry is a well-known fish biologist from Canada. I've been to the Canadian Society of Zoology meeting earlier this year. He's worshipped there. So he was the first one to actually measure a critical oxygen level in goldfish, and he measured it across a temperature range. He also measured active metabolic rates and these resting metabolic rates, and coined the term aerobic scope as the difference between the maximum metabolic rate and the resting metabolic rate. And that was thought to be the amount of oxygen you had available to you to fuel all of the activities that you do. And as you go higher in temperature, that aerobic scope tends to increase and reaches a pinnacle that is thought of as an optimal temperature, and then it falls off at higher temperatures above that. And that's termed, generally thought of as oxygen limitation that causes that decline at higher temperatures. Kleiber first discovered that metabolic rate is related to body size, the famous mouse to elephant curve. Elephants have much lower oxygen consumption rates per gram of tissue than mice. And he postulated that that was oxygen limitation at large size as well. So these ideas have remained pretty much intact, but have been now applied to climate change and every other thing you can imagine. Most famously by Hans Portner, who's one of the lead authors of the IPCC report, has his favorite theory, the oxygen and capacity limited thermal tolerance idea, which takes Fry's aerobic scope idea and applies it in a climate change context. Daniel Pauly has been pushing a Gill oxygen limitation idea that says as you warm up, metabolic rate increases and you run into a constraint where you have these two-dimensional surfaces like gills that can no longer meet the requirements of the three-dimensional body that's consuming the oxygen. So he thinks with climate change, we're going to get a bunch of smaller fish. And of course, the metabolic theory of ecology suggests that, again, that body size, the metabolic scaling, this mouse to elephant curve, is caused by oxygen limitation, and they've postulated a mechanism due to fractal scaling of blood vessels and things. Was a big splash in the late 90s, and they've then applied that scaling curve to all sorts of ecological problems. So recently, in collaboration with Curtis Deutsch, I published a metabolic index, which is a simple ratio of oxygen supply to demand. Here, oxygen supply over demand, which always equals 1. And the idea was that if you can have this very simple ratio, how much oxygen is available, how much do you need, in an environment where there's plenty of oxygen and your demand is low, you've got this aerobic scope for activity. And as you get warmer and warmer, that aerobic scope declines, or as oxygen is reduced, that scope declines, and you'll reach some critical limit that you can compare to species distributions and make some predictions about how populations will shift as the planet changes. So oxygen supply can be thought of as a function of the physiological oxygen supply capacity. So this little symbol alpha is the hearts, the gills, the blood, the mitochondria, everything you need to extract and transport oxygen to the points where it's used. And I've presented this, like I said, at the Canadian Society of Zoology, as well as 2 other physiology meetings this summer. And physiologists hate it when you reduce their entire lifetime work to one symbol. And then in a few steps, I'm going to cancel it out, and they really hate that. So, so once you have the physiological supply capacity, then you have the environmental oxygen availability. Demand is simply the metabolic rate. So how do we get at alpha? So at the critical oxygen partial pressure, the oxygen supply capacity is maximized. Your heart rate is going full blast, your ventilation is going full blast, you're transporting as much oxygen as you can to maintain that resting rate with little available oxygen. So if we know P crit, the critical oxygen partial pressure, we can calculate the oxygen supply capacity. So in this example, you've got a resting or basal metabolic rate of 3, and they can maintain that down to a critical oxygen level of 6 kilopascals. So rearranging this equation, you can calculate that the oxygen supply capacity is 0.5 micromoles per kilopascal available. So that seems pretty straightforward. And then I went out to sea in November last year, and as I'm walking on the boat carrying a bunch of equipment, it occurred to me that this should apply not just to the critical oxygen level at the resting rate, it should apply to the critical level at any rate. If you're swimming faster, you've got a higher rate, and you'll reach some critical level, higher critical level, and the maximum rate. So nobody measures the rate between basal and maximum. So I've been estimating maximum metabolic rates. So if you assume that this oxygen supply capacity is true along this entire curve, then you can calculate what the maximum metabolic rate would be if you are in air-saturated water at 21 kilopascals. And it would predict that you would have a maximum metabolic rate of 10.5. So this is a sort of hypothetical example, but what we don't know, so this is a hypothesis basically, that this oxygen supply capacity is the slope of this curve, and that it's equivalent under maximum exercise as well as resting in hypoxia and everywhere in between. So that's the hypothesis, and here's where alpha just cancels out, and you're left with this equation. But we don't know what this P crit for the maximum metabolic rate is. That's a critical point. So could be much higher, could be lower. We don't really know what this point is. It's never measured or rarely measured. So, but we can rearrange this equation and calculate it if we know P crit, the maximum metabolic rate, and the basal metabolic rate. So I went to the literature and I found 50 species, and that's all there is, trust me, been looking, that have all 3 of these metrics measured. So these include arthropods, mollusks, and chordates from terrestrial, marine, and freshwater habitats, hypoxic, some of them are in persistent hypoxic habitats, the rest of them I call normoxic, I'll come back to that, across a huge temperature range and across 5 orders magnitude size range. So humans are in here, alligators, insects, squids, naked mole rats, the ugliest animal on the planet. So 13 of those 50 species are from persistently hypoxic environments. That is, they never see air-saturated, they never see atmospheric partial pressures of oxygen. So they're from estuaries, or at least seasonally they don't see air-saturated water. High altitude, ponds that, again, seasonally go hypoxic or anoxic. The naked mole rat lives underground where it's persistently hypoxic. And then animals in deep sea oxygen minimum zones. So we did this calculation for those 50 species. For the normoxic ones, 37 of those species, the mean P crit maximum, the critical oxygen level at maximum metabolism was precisely air saturation. And for the hypoxic species, it was consistently lower. So we interpreted this to mean that all species basically evolve an oxygen transport capacity that can take the oxygen that's available to meet whatever metabolic demand ecology has inflicted upon them. So they've evolved an oxygen transport capacity that matches whatever they're doing. So this would get away from the idea that oxygen is limited at larger size and fish are going to shrink, or that metabolic scaling is caused by oxygen limitation. So this critical oxygen level for maximum metabolism, these are those 37 species at air saturation. For the 13 species, it correlates very well with the maximum environmental oxygen to which they're exposed. The P crit doesn't correlate. The lowest ones in the deep sea oxygen minimum zones do have a lower critical oxygen level, but in general it's a much poorer correlation. So P crit max is effectively the environmental oxygen that animals have available to them. So we can substitute that environmental PO2 in for P crit max and then calculate the oxygen supply capacity as either basal metabolic rate divided by peak crit or maximum metabolic rate divided by environmental PO2, and there's a perfect correlation between them. So I actually had to expand the significant digits on my graphing program so it didn't say R squared equals 1. So we can rearrange the equation again and calculate the maximum metabolic rate. So this is the measured versus the estimated or calculated maximum metabolic rate for a variety of species, with humans and grasshoppers up here toward the top, and a variety of other alligators and rock lobsters. So again, a very good correlation. So my first thought when I realized that I could calculate maximum metabolic rate was that I could put Loligo Systems out of business. They're the ones that make all the equipment that you use to measure maximum metabolic rate, and they are horrible and expensive. So, but I don't know if that'll actually happen, but it's still a goal. So across temperatures, the prediction holds. So at any temperature and any body size, you can calculate the maximum metabolic rate. So the dashed lines, I forget which is which, dashed is estimated and solid are measured, but they fall right on top of each other for a variety of fish species and an alligator. And so we can test this oxygen capacity limited thermal tolerance idea that Portner and others have championed and that Fred Fry first came up with nearly a century ago. So again, across the temperature range, the dashed line are the measured maximum metabolic rates. The solid lines are the estimated. And so when you get to a high temperature, the measured maximum metabolic rate falls off, but the estimated continues upward, which tells me that this is not due to oxygen supply. This drop off here is due to some other effective temperature. Once you're beyond the temperature range you live at, there's no selection for maintaining any system. So it could be nerves, muscles, anything. But it's not oxygen supply because that would also affect the critical oxygen level, and then this curve would follow that one. So for black sea bass, measurements that we made over the last few years, and for the goldfish, the original data from 1937, neither of them appear to be oxygen limited. And this is just showing the same thing, but for aerobic scope instead of maximum metabolic rate. So this ugly equation is just the same equation, but now I've added temperature and body mass coefficients. So by rules of exponents, if you're dividing exponents, then you subtract them. So the temperature coefficient for maximum metabolic rate minus the temperature coefficient for basal should equal temperature for peak crit max minus the temperature coefficient for peak crit. And same for the body mass scaling exponents. So we can predict the maximum metabolic rates at any size and at any temperature using these formulas. So this is the data for black sea bass. So the temperature coefficient for peak crit max is 0 because they're always in air saturated water. So it's 21 kilopascals regardless. So that doesn't change. The maximum metabolic rate plus the temperature coefficient for peak crit equals the temperature coefficient for basal metabolic rate. So the resting metabolic rate tends to increase with temperature faster than does maximum. And peak crit just sort of follows along. So you can extrapolate out to very high temperatures. So this is where maximum metabolic rate actually falls off and the calculated peak crit max falls off. But if you extrapolate those up, you can find the point where maximum and basal metabolic rate would meet, because basal is increasing a little bit faster than maximum metabolic rate. Where they meet, you've got no more aerobic scope, so you can't have anything other than resting metabolism at that temperature. But it's way higher than any temperature they're ever going to see in their environment. So aerobic scope is not limiting. And peak crit at that same temperature meets air saturation. So at that point, there's just no excess oxygen beyond what they need for the bare minimum maintenance metabolism. So absolute aerobic scope, which is maximum minus basal, goes up and then falls off at that high temperature here. Factorial aerobic scope, which is maximum divided by resting, reaches 1 at that same temperature. So these are the predicted temperature coefficient for resting metabolism versus the measured across a bunch of different species. And again, a very good correlation. This is the basal or resting metabolic rate versus maximum. And for each species, within a species, that resting metabolism increases faster than maximum. But across species, they don't. So across species, resting and maximum metabolic rate increase at the same rate, but within a species, they increase faster. So all of the variation in supposed hypoxia tolerance is really just adjustment for temperature and has nothing to do with oxygen. That'll become a little more clear in a minute. How am I doing for time? Going fast. Stay with me, sort of. A lot of equations, I warned you. So these are the normoxic species in blue, each point a different species. The maximum metabolic rate as a function of the oxygen supply capacity. The hypoxic species have a higher oxygen supply capacity over an equivalent range of maximum metabolic rates. So oxygen, the low oxygen that they live at is not limiting their maximum metabolic rate. They just evolve a better oxygen transport system. So this is the critical oxygen partial pressure for all of those normoxic species, and it ranges from 12 down to almost 2. It's a lot of variation, and historically people measure the critical oxygen level, and if it's low, like around 2 or 3, they say, oh, this is a very hypoxia tolerant species. It must experience hypoxia somewhere in its environment, but they don't know where. They don't have any evidence. They just say it must have evolved that for a reason. But what this tells you is that all of this variation is due to factorial aerobic scope, maximum divided by basal. So if factorial aerobic scope increases, the critical oxygen level has to go down. P-crit max is always 21 for these species. So if you have a critical PO2 of 7, you've got a factorial aerobic scope of 3. For the hypoxic species, the same is true, but with a different P-crit max. So what this looks like across species, critical oxygen level goes up with temperature, factorial aerobic scope goes down with the exact same slope, but opposite in sign. And because factorial aerobic scope times the P-crit has to equal 21, this red line is the square root of 21, where those two metrics should be equal to each other, and they are. So these are 3 different species living at very different temperature ranges. So depending on where you compare them, if you compared at a common temperature of, say, 30 degrees, you would conclude that the coral reef fish is much more hypoxia tolerant than the black sea bass. And that's actually been published that that's true, when in fact it's not true at all. If you compare them at the same point within their range, they have the same critical oxygen level. So hypoxia tolerance, as we've always defined it, has nothing to do with hypoxia. It has to do with temperature. So I've been measuring critical oxygen levels for my entire career, and now they don't mean what I thought they mean. So this is just showing that the factorial aerobic scope is equivalent to 21 divided by P-crit for all those species. So same idea. All right, so how does this work? If you have, say, a sluggish benthic species and it evolves into, or you want to compare it to a fast-living pelagic species, selection acts on that fast species. It acts on the oxidative and muscle capacity to meet its new ecological demand. It has to swim all the time. So it has a higher maximum metabolic rate at the same oxygen level. And simultaneously, selection acts on the oxygen transport capacity, so the slope of this line. So it jumps from 0.5 to 0.71 in this scenario. So the pelagic species has a higher oxygen supply capacity, and the basal metabolic rate will either stay the same at a lower P-crit or jump up at the same P-crit. Because there's all this additional muscle mass in the pelagic fast swimming species, it results in a higher resting metabolic rate. So maximum and resting metabolic rates are necessarily linked in this way, which gets at another hypothesis that's been debated since the 70s, which is that there must be a link between resting and maximum metabolic rate in order for endothermy in vertebrates and birds to have, in mammals and birds to have evolved. I won't dwell on that. So those two are linked. If you have one species, but its maximum metabolic rate increases with temperature, like the black sea bass data we have, the oxygen supply capacity increases as temperature goes up. But rather than basal metabolic rate just going up at the same peak crit, basal metabolic rate increases faster than maximum, and that's the only reason that peak crit changes with temperature. Okay. So quickly, this is data that my student Alyssa has collected for juvenile bull and blacktip sharks, and it's sort of an interesting exception that proves the rule. So these are species that are, the blacktip shark is an obligate ram ventilator. That means it has to swim in order to aerate its gills. The bull shark was thought to be not obligate. It's able to sit on the bottom and rest and pump its gills and be fine. But this data shows that when they are sitting on the bottom, their resting metabolic rate is lower, but so their peak crit is higher. They're not meeting their metabolic rate as well as they do when they're swimming. So they can't sit here on the bottom for very long. They can do it for a little while, but then they have to start swimming to pump, to get water across their gills. So that's pretty cool. This is an annular respirometer that Alyssa has built, and it's down at Moat Marine Laboratory. So it's a juvenile shark that swims at its own speed around this tank, and she can measure oxygen consumption while it's doing that, maintaining temperature and oxygen levels. All right, so in hypoxia, same idea, but instead of increasing maximum metabolic rate, you just increase the oxygen supply capacity. There's no increase in resting metabolic rate, you just get a lower peak crit. So that's evolving or adapting to, skip that. Last point, if you decrease oxygen, you can precisely calculate what your maximum metabolic rate will be. Your maximum metabolic rate will decrease exactly 5% per kilopascal. And so we can predict what humans do when they're exercising in altitude, and we can predict what sharks do when they dive into an oxygen minimum zone. So I will stop there.